is a full professor in chemical engineering at the Norwegian University of Science and Technology and NTNU in the beautiful city of Trondheim since 1987. So I put one picture of the NTNU and of the city. And he received his Master of Sciences degree in Chemical Engineering at NTNU in 1978 and the PhD degree from the California Institute of Technology in 1987. His supervisor was Professor Morari. I found this picture in the internet that SIGURD had prepared the document, and it's a very Californian, you see, style, so I like that very much. I put it. Professor SIGURD is the author of more than 200 international journal publications and more than 200 conference publications. He is also the principal author of the book Multivariable Feedback Control that was published by Wiley and has 2 editions. He has graduated more than 40 PhD candidates, and he is the director of SubPro that since 2015, which is a research-based innovation center in subsea production and processing. So Professor SIGURD has many titles, and he is very, when we think about process control, we remember his name, and when we think about NTNU, we also remember him. And he, I think he likes to collaborate with different groups around the world. We in Brazil have been in contact with him. I think Jorge Trivale told me that maybe his first time in Brazil was during the ADCAN in 2006. And so we have a picture here from that Congress. Professor SIGURD is here. And also more recently, we had this meeting at UFRJ where we can see him here. Here you can see Ajimiro is also here. Yes, here. I am here. So we are very glad that he can dedicate his time to collaborate with us. Today, he will present this conference entitled Nonlinear Input Transformations for Disturbance, Rejection, Decoupling, and Linearization. So I would like to thank him very much for being here. And he will make a presentation of around 45 minutes, and then we will have the questions and comments in the following. Thank you, Professor, and the word is with you. I will end my presentation. There are some people entering, and I'm also giving the allowance, but I will stop the presentation. Yes.
Okay, good.
Thank you.
So now it's better. Okay, so thank you very much for inviting me. I'm very happy to give this seminar. It's on a topic that I've been working on for not that long, maybe a bit more than 1 year. It's a topic that I think has a lot of promise because it can, I think, be very practical, and it makes use of the model, nonlinear model, directly to derive control structures. So I'm doing this to work together with my PhD student, Kristina Sotika. She is also online at the meeting now, I saw. Also, thanks to Nicholas Alsop and Christian Holden and 2 master students who are working on this. So before I just show some pictures from Trondheim again, you showed already Maurizio, but some more pictures from also Norway, showing how far away Norway is. You know, you see it's just south of the Arctic Circle. Here's the Arctic Circle. So it's this is how the sun looks in the summer, or when at midnight, or in the winter at the middle of the day. It doesn't get any higher than this in the winter, or slightly higher maybe. Anyway, so it's good to be in Trondheim. You know, it's far away and very quiet here, so we can work. You mentioned most of my CV, so I will not repeat this again. This is my career. Also have some non-professional interest. One is mountain skiing, cross-country skiing. Another one is orienteering, so running around in the wood with a map. And the third one is a bit of hunting for birds, for grouse hunting. Anyway, let's get into the talk. And I have my homepage, which has mint from 1996, still running. And there you can find one quote from me that the goal of my research is to develop simple yet rigorous methods to solve problems of engineering significance. So that has been my goal for my work, to combine theory and practice. Sometimes I feel that this picture is showing you a good picture of how I sometimes feel. You have this fish pond, you see lots of fish are going in one direction here, all the blue fish towards the direction of optimal centralized solution. And there's one fish here going in another direction. Simple solution that work in practice, PIDs and so on. And that fish, I think, seems to be me. But I hope more fish can be joining me. Now, what I present today, I think, is not really so much in the wrong direction. It also has a lot of uses a lot of things that have been presented by people in control theory. So, to the introduction of the topic, so is that I have observed from industry that they frequently use model-based calculation blocks. And they also use a lot of cascade control. But when I look at what they've done and I ask them why, they don't have a good answer. There's not really any theory behind what a lot of things they do. So I've been searching for this theory, or getting a better make it easier for the engineers to use the right things. And one idea then is to use nonlinear model equation derived control strategy, or you can say to derive control structures with embedded knowledge through input transformations. And as you will see, this is very much related to what's called feedback linearization. That's a nonlinear control theory that became popular around 1990. It has not been used a lot in process control. So the primary use of what I present today will be in nonlinear feed-forward control and nonlinear decoupling, and also insight into how to use cascade control. So now comes a slide. I think that's very important. It gives you essentially the main idea of everything. So I think you should concentrate on this slide and try to understand what I'm doing here. And if anyone has any questions, actually they can ask about this one. So the main idea is really, I will say, trivial, but it's almost magic. So assume that you have this process given in red here. So you have a nonlinear dynamic model. The y dt is a function, nonlinear function of the output y, the input u, and the disturbance d. And now what you do is introduce some transformed inputs called v. So the original inputs are u, and I make some transformed inputs v. They are simply equal to the right-hand side of the model equations minus a times y. A is a tuning parameter. You can select it equal to 0, then you get feedback linearization, but more generally, it should be non-zero. So the thing is, if you introduce this simple transformed input, then you get your new transform system, which is shown by the blue box here. So this is the transform system after introducing this input transformation. And this system looks like this. It's dy dt equal to ay plus v. So if you look at this system, it's first thing, it's linear. It's first order. It's going to be decoupled if A is diagonal. And it's independent of disturbances. So it's, as I said, it's almost magic. And how do you make this work in practice? Well, you need a static calculation block. That's this block here, which from a given value of v, from a known value, from a measured value of disturbance, also based on the measured value of y, will compute the input. And that's really just inverting this equation here. So you need to invert this equation for the transformed input. So you have given v, You measure y and d, and then you can calculate u by solving this equation. So we'll get back to how we can solve these equations. It can be analytically, it can be numerically, and it can be by feedback. And the value of v, that's this value that comes in here, that's computed by a conventional controller, often a linear controller, for example, a PI controller. And for perfect disturbance rejection, you don't even need this controller. You can just keep v constant, and then you can see from this equation that you have perfect disturbance rejection through this static calculation block here. So it's almost magic. There are some assumptions. Of course, the first most obvious assumption is that you need to know the model, and you need to measure the disturbances. So that's not often the case, but if you cannot measure all disturbances, it can still be useful. We'll see that. Another restriction in the way I put it here is that you need as many outputs y as you have inputs u. So clearly this is restrictive, but we will lift this restriction later. And also you must assume that the solution to the static inverse problem, so the solution in this block here, that this solution exists and satisfies certain properties. And the main property is that there's no singularities within the domain of interest. Okay, so I told you this is very similar to feedback linearization. Any questions, by the way, so far? Are you hearing me?
Yes, Sigurd, you're.
Okay, so do you have any questions so far, Maurizio?
No questions.
Okay.
So far. Okay.
Okay, so this is really the main idea. So it's almost magic. You do this transformation, you have perfect feed-forward control, and it's very similar to feedback linearization introduced by Isidori in the 80s. So you can see it's essentially the same thing. The only difference is that in feedback linearization, usually this function is usually assumed to be linear, affine in U, and also usually make the A equal to 0, such that you get an integrating system. So the name of this is called feedback linearization, which I think maybe is a bit misleading if you look at what it's doing. Maybe a more descriptive name would be that it's nonlinear static feed-forward control and linearization with a little feedback. But feedback is not really the main thing here. The feedback is this y here, but actually that's not the main component in this inversion here. So the system is mainly inverted by static inversion of the nonlinear model f, and the most important property probably for practical use in process control is probably that it eliminates disturbances in a nonlinear way. So it's because feed-forward control is not used that much in process control. Now, one important reason is nonlinearity, but this approach will actually correct for nonlinearity. Yes, there is some linearizing feedback from y, but not necessarily a lot. So let me look at these extensions that we have done compared to feedback linearization. So the first extension is that we looked at a bit more general function for the right-hand side. Normally in feedback linearization, it's assumed to be linear or affine in the input, so seems a bit limited. But this assumption is not really necessary. It has some advantage, of course, when you do it this way, because then you can actually explicitly find the solution to this inverse, at least for the scalar case. But we will in this talk have the more general function, and then a transformed input will be, as I said before, the right-hand side minus a times y. And we may need to solve this thing numerically and not analytically. But that's not really a problem. Actually, I wrote an email to Isidori and asked him about this, and he said that originally they did allow for more general right-hand sides, but for some reason they made this assumption in the paper. But I think he agrees that it's not really necessary. And the second thing which has puzzled me a bit is why they make this transform into integrating. So this is by choosing a equal to 0, you make it integrating. But if you think of what it's doing, it doesn't make maybe too much sense, because so by choosing a equals 0, you make this linear transform system into an integrator, okay, from v to y. Make it as shown here. This is how it looks. The y dt is equal to v, pure integrator. The disturbances are eliminated. But if you think about what you want to do afterwards, you're going to design an autocontroller. You need this autocontroller also, because there's going to be disturbances you don't measure. There's going to be model error. You will need to have a feedback from the measurement y and compare to a set point, having conventional PI control to do this correction for uncertainty. So what you will do then, if you make it into integrator, assume that you have a fast process and you want to have fast control. So first you will use a positive feedback essentially to make this system integrating. And after you made it integrating, you will use a fast feedback, negative feedback, to move the dynamics back again to maybe close to where they were originally. So it doesn't really make any sense that you first move it into the integrator and then move it back again. So I think this is a limitation which is not really necessary. Another thing is that integrating systems are not easy to control. They are more difficult to control than just first order systems, at least if you want to add integral action to the controller. If you only have proportional control, there's no problem, but if you want to have integral action, which you usually want, then there's the limitations here. Also, so I think this is something that is not necessary, to have this integrating. I think they did this for the feedback linearization theory just to make it simple, to show that you can do these transformations, but it's not really necessary. So the extension 2 is to introduce this tuning parameter A. So as I showed before, this is the original system. It transforms input VA, and you get the transformed system, which is linear and first order. Oh, here. So A can be used to get the desired dynamics, and the system will be decoupled if this parameter A is diagonal. So A equal to 0, that corresponds to feedback linearization. But one general idea is to select A equal to the derivative of f, the right-hand side, with respect to y at a nominal operating point, because then normally the transformed system has the same dynamics as the original system. And there is normally no feedback from y to this block here, this input calculation block. So this might be a good choice. But you can also use it to speed up the response and get any dynamics you want, really. Except, of course, you need to be careful if there's delay in the measurement and you speed up the response too much. Of course, you can have problems with instability. There's a close related transformation that we presented at the IFEC World Congress. And that's to take instead of taking VA as the F minus AY, you multiply this by minus A inverse and get this as your transformed variable input, Y minus tau 0, which is minus A inverse times F. And then you get a transformed system which in time constant form. And the difference now is that with this transformed variable, that you always have a steady state gain of identity matrix, which means that at steady state you have Y equal to VA0. This should be a subscript, VA0 here. So it's very similar, but it has some advantage at steady state of making a steady state gain of identity. And then we may, in theory, avoid the auto feedback controller completely. But that's only if you have no model uncertainty and you have measured all disturbances. Again, as I said before, the auto control is needed to correct for model errors and unknown disturbances. But in theory, you can, with this related transformation, get away with the output this feedback controller C completely. Okay, so then another extension compared to feedback linearization is to consider static systems, which are actually very important in process control. So static systems, you typically have a set of equations, nonlinear equations, and you select maybe one of them or a couple of the states X are outputs. So this is very common, and this is not covered by the normal theory of feedback linearization, these systems. But it's actually very simple to handle these systems in a similar way. What you can do is you solve these equations with respect to X, and then you eliminate the X's and put them in here, and then you can derive the relationship directly from U and D to Y. So you can write the equations on this formally. Now all you need is to just introduce R as your new transformed input, V0. So, and then the new transformed system is going to be linear, static, and independent of disturbances. So the new transformed system is just Y equal to V0. So this is similar to what we did before, but with transform system, with a static system. So what you note here is that this V0 is actually independent of Y. There's no, see here, there's no arrow from Y here into this block. And you see also from here, V0 is independent of Y. So the inverse input block is actually a purely feed-forward block. So this is really simple nonlinear static feed-forward control, which people have applied many times before. But I'm just putting it into the same setting as feedback linearization. Of course, we need to assume that the solution to this static inverse problem exists and is unique, but this is usually satisfied for physically real systems. And if you have problems in solving them, you can. I will talk about an extension 5 later, which is a trick that you can solve the equations by feedback instead of doing it numerically, using an I controller, purely integral controller. And this may actually be a safer approach in many cases, because it's like a continuous solution of the equations. Okay, so then let's look at some examples. So I call this magic because you're going to just get some fantastic responses here. Look at 3 examples. First the heater scalar, and then I look at an example with 2 inputs and 2 outputs, and finally a static model, a heat exchanger. So let's first look at the electric heater. So what we're doing here is simply heating water, or whatever. So here's the feed. It's heated in this tank, and this is the product going out, and it should have a certain temperature. I'm assuming constant level, but that's not really important here. So if we write down the energy balance, this is written here. So you see the output is temperature. The input, well, we haven't really decided yet. I know it doesn't matter for actually to begin with. So this is the right-hand side of the equation. I mean, define the transformed variable to be equal to the right-hand side minus A times T. So A is the tuning parameter. And the transformed system then is going to be linear, and it's going to be independent of disturbances. So simply a linear first-order system. That's this block here. So the choice of the tuning parameter I mentioned before at the recent value is to choose it equal to the nominal value of the df dy. So that's going to be minus q divided by v. So it's minus 1 divided by the nominal residence time. And if you look at this value, if I put a equal to minus q divided by v, you will see that the q divided by v here and the q divided by v nominal here. So actually, nominally there will be no feedback from t. Nominally you will just have this expression for VA, for the transformed input. So that's at least one possible choice for the tuning parameter. We minimize the feedback from into the transformation. So in the input transformation now, the inverse transformation depends on what u is. So actually we didn't need to make a choice of what u is when it did this, but if u is equal to the flow, so this is the input. So you're controlling the temperature by adjusting this is the amount of cold water coming in. Then you get this expression for the the inverse transformation. And here you can see there is some singularity possible if T0 is equal to T. So if the feed temperature is equal to the product temperature, it makes sense. Then of course, it doesn't make any sense to be heating it. If you're heating it and then it's it has the same temperature out as in. So of course, this is not going to be working. The only way you can make it work is let it go to infinity here. So, but let's look at the other choice of input, another one. That's going to be the heat input. So here you get this expression for the inverse. So this is always well behaved here. You can see that the input will depend on the value of VA computed by the controller. And so disturbances here will be the Q and T0. And there will be some correction, essentially feed-forward action from disturbances into the input Q. Now let's look at some simulation for the second case here. So the input is equal to the heat, and I want to control the temperature in spite of disturbances in the flow in and in the temperature in. So here I'm showing you the simulations. So we have first a disturbance at T equals 100. There's a disturbance in T0, and you see VA is kept constant because we want to keep a constant temperature. So VA we're not using the autocontroller at all. This is showing you, so it doesn't use the autocontroller at all here, but it changes the heat input based on just the feed-forward action from T0. And the temperature is kept constant. So then at T equal to 2000 here, we have another disturbance. That's a disturbance in the flow rate into the tank. Again, so again, so the heat input, the flow rate goes down to half its value, and heat input goes down to half its value, just by feed-forward action from this expression here. This is the inverse input block. Finally, at T equal to 4000, I make a set point change, and then I'm actually using the autocontroller to do this, to generate a change in V. So that's the change in V generated by the autocontroller. And this is the corresponding input you get, and this is the temperature. So you can see it's almost working like magic here. It looks almost too good to be true that the temperature is completely constant and the VA is constant. Well, the reason for this is, of course, that we have a perfect model, and I assume that we have perfect measurements of the disturbances. Now, in practice, we may not have all disturbance measured. For example, assume that I don't measure this disturbance in T0. I can still use the transformation, but instead of changing T0 based on the measurement, I can just keep it constant, for example, at 10 Celsius, nominal value. So I'm showing you that in the next simulation here. So the solid line, that's what we saw before. And the dashed line is not without the measurement of T0. So now I need to use the feedback controller to correct for this disturbance in T0. So what you will see is that that's why it starts. It takes some time before the feedback controller takes action, and you see it changes the VA, the outer feedback controller, and brings it back again. So the second disturbance is handled better because this is handled by the feed forward, you could say. So this is handled better, and the set point change is a bit similar to how it looked before. So here you can see we are using the outer controller because you can see here this is the outer controller that's correcting for the disturbance that we did not measure in this case. Okay, so this was example 1. So let's go to another example. So this is an example of a shower where we mix 2 streams to control the temperature of the mixed stream and the flow of the mixed stream. And the input is the flow of stream 1, which can be the hot water, and the flow of stream 2, which could be the cold water. So the mass balance is assumed to be static here. So this volume is constant. So as soon as you put something in here, it comes out there. So it's a static mass balance. The total flow is Q1 plus Q2. The energy balance is dynamic, and this is just an energy balance here by mixing two streams. So here we can define one transformed input for the static equation as we did before, just as the right-hand side here, and one equation for the dynamic equation as the right-hand side minus A times T. And A again is going to be equal to the minus Q divided by V, the nominal minus 1 of the nominal residence time. So if you take these two equations here, they are coupled, but you can solve with given value for V0 and VA, you can solve them and find Q1 and Q2. So Q1 is this expression, and when you found Q1, you can put it into this one and find Q2. So here again, you see some problem with possible singularity if T1 is equal to T0. But again, of course, it makes sense if you have T1 equal to T2, there's no way you can control the temperature. Then you have the hot and cold water at the same temperature. So it's not really a limitation in the transformation, it's more a limitation in the system itself. But of course, you have to look out for things like this. So let's look at how it behaves in simulation. So here's the simulation with transformation only. So we're not using any feedback controller on the outside here. And you can see here we have disturbances first in T1, the temperature of the hot water, then the disturbance in the cold water, and then we make a set point change in the temperature of outstream and the total flow. And the way we do this is for 1 and 2 we keep V0 and VA constant, and for 3 I make it step in the VA, and for 4 I make a step in the total flow V0. And you can see it's behaving like wonderful here. So we have the disturbance. This is how the hot and cold water is changing. The temperature remains constant for all the disturbances. And when you do this step change in, this is the flow. It remains total flow remains constant, and the temperature remains constant. This is for the step change in temperature, and you see it follows the residence time of the system. And the flow is changed immediately when you make a step change. So again, this is working wonderfully. Now you kind of course, wonder how well it behaves if there's uncertainty, but we have looked at a lot of cases with uncertainty, and it behaves surprisingly well. Of course, if it gets too much uncertainty, it will not work that well, but there's no big surprises that we have seen so far. So then look at the third example of a heat exchanger, a static. So this is just a heat exchanger that is countercurrent heat exchanger, and we want to control the outlet temperature using the flow of cold water to control the hot water temperature. Now the equations here are actually very nonlinear, especially if the cold water is the input. You see it enters into some exponents here. So this is the expression for the hot temperature. This is sometimes called the epsilon NTU model. So this is actually very nonlinear model, and it's not easy to solve. So what we did when we did, so we have this, if we're given V0 and we want to find this FC, we solve these equations numerically. And I'll show you now how it works when we apply them to dynamic model. So this is essentially static feed-forward control, nonlinear feed-forward control. Here you see for disturbance in this cold water temperature you see that the temperature is going back again. Essentially, it's reacting immediately based on the feed-forward action here. The reason, of course, temperature is not staying at its desired value all the time is because we are applying it to the dynamic model. And the reason there's some steady state offset is because the dynamic model actually is not quite equal to the static model. In the static model, we assume delta T log min, but the dynamic model is a cell model which doesn't quite follow delta T log min. But you see it's behaving very nicely, as you would expect. Here's for disturbance in the TH in. So here there's like a bit of delay. So you have a disturbance here. It will take some time before it affects this one. But the feed-forward control is changing it immediately. That's why we're getting this inverse response there a bit, in the or wrong response in the temperature. Otherwise, it's behaving very nicely. And finally, here's a set point change. And again, this is using the outer feedback control, and it's behaving nicely. So the one, so this is working great, all of this. But one big limitation here is that it assumes that we have as many inputs as we have states, and this needs to be solved or to be avoided, this assumption to apply to many practical situations. So you could use feedback linearization and get a chain of integrators, but it's not very easy and it's not very practical. So what we propose to use is simply to assume that we can have additional measurements. So if there's additional states that enter into the right-hand side, given by this variables W, we assume that we can measure these variables, and then we can almost do the same as we did before, introduce the same transformed variables, and we get again a linear transformed system. But how do we invert a transformation? That's a bit more tricky here. Now, if f depends on u, like here, then we can essentially do that we did before, although it may be a bit dangerous because there could be right-hand plane zeros, unstable dynamics here, internal dynamics. Now, in some cases, actually, u does not enter into this one. So then you cannot solve this expression for u as it did before. But for example, one way is to solve it for w and then use cascade control of w. Another approach is to use a chain of inverse transformation, and this can be applied if you know the dynamic model for w, like given here. Or the third option, maybe the most general, is to use cascade control of this v variable. So I'll show you how this can work. So here we have the process, and here we don't have the inverse block. This is just a block that computes v. So this is the v variable, and we assume we measure this w, we measure the y, measure the disturbance. Then we know this, and we also know the input. Then we know the right-hand side, and we subtract a times y, and we have this calculated value of VA. Now, the set point for VA is computed by this controller, and we just have a slave controller now that changes u until v becomes equal to the set point. So this controller is tuned based on experimental response from u to the calculated v, to includes the possible w dynamics here. And if the slave controller can be made sufficiently fast, this will be the same as inverting the static input transformation. But otherwise, there will be some loss, of course, because the slave control is not infinitely fast. There might be also all the other reasons why you want to use cascade control, and that's mentioned here. There might simply be that there are some unknown parts in your right-hand side that you can measure. There can also be that you cannot invert the calculation. This inverse calculation is difficult, so you can use cascade calculation block as a trick, cascade control as a trick to solve this input transformation. I mentioned this before. That's what I refer to extension 5. Or you may want to slow down the inversion. For example, for the heat exchanger, you may want to slow down the inversion a bit, and then you can actually put the heat exchanger equations in here and solve them by iteration. And by having this slow control, this slave control a bit slow, you can make it, the whole inversion, be a bit slower. So there's many possibilities here. So maybe that's one of the problems. There's many ways you can do these things. So if I take another example here of a CSTR, so here we have one input, that's the heat input. So I want to control the composition using the heat. So that's a bit indirect, because the heat input does not really affect composition directly, as you see from the component balance. composition, the heat input only affects temperature, and temperature indirectly affects composition through the reaction rate constant. This is a bit indirect. What we can do here, for example, is also you note here that the Q does not enter into this equation. I cannot solve this equation with respect to the Q input. But anyway, the transformed input is going to be the same as before. The right-hand side of this first equation, minus A times CA. We have this extra measured variable, W, which is the temperature. Tuning parameter as before. And then I'm going to show you how to use cascade control to solve this. So the first way of doing cascade control is to solve this using this, where I just calculate the right-hand side and then use a slave controller and change the heat input until this calculated value is equal to the set point. So that's the one approach. But there are also other approaches. We could use cascade control of W here, of temperature. In this case, we need again the static input block. So we need to solve this right-hand side here with respect to temperature, which will require some calculation. You get some expression here, which is a bit complex. It's not difficult, but it's a bit complex. So we put that in here. We get out the temperature from the set point from temperature, and then have a slave control for the temperature. So it's an alternative implementation of this cascade. Now the simulation I'm showing you here is for this alternative implementation. You can see again it's working nicely. This is for a disturbance in T0. So T0, was the feed temperature. This is the disturbance in the feed composition. And you see that it's for these disturbances, the outer feedback controller is almost doing nothing. But again, for the set point change, it needs to make a change in the V. There's also a third option here, which is to use two inverse static input transformations. So then I make use of the fact that I know the model for dt. I didn't make use of that before, actually. Before I just used feedback, I didn't need to know this model. But if I know this model, I can use this as well. This might have some advantages, but I doubt in this case it's going to be worth it, because this gets quite a bit more complicated. But this is something that we are working on, comparing these different alternatives. So let me also show another way we can use this insight from the equation to design control structures, which are more close to what people are doing in practice. So let's look at the level control problem. So we want to control the level here using the flow out. So the input is going to be the valve position. So we can make a nonlinear model here. We have the mass balance is very simple, just the dV dt, that's the volume of the tank, is Q in minus Q out. So I want to control the volume, that's the output. And we have a non-linear expression for the flow out, and this is the valve equation, which is non-linear. So this looks a bit complicated. We could use our standard method, and define this f function and then do VA and invert this and so on. But this gets very complicated. Now, the insight that you can use here, if you're a good engineer, you see that, well, maybe this Q out we can measure Q out, and I don't need to use all this complicated model here. If I just can measure Q out, this can be like a W, and then I can just use the cascade control, similar to what I did on the last example. So because what I do now is that I will show you here. So you have the static input transformation. We compute V, which is Q in minus Q out. You remember V here, that's the right-hand side of these equations here. But this is an integrating process, so we choose A equal to 0 here. So it's already integrating. Then we have a slave controller, and the slave controller adjusts the valve position until this computed V is equal to the set point. So if you look at how it looks in the block diagram, now this is a block diagram in the flow sheet. We'll have a level controller being the master. You have a flow controller below, and this static input transformation is just this place there where I take Q in minus Q out. That's this thing. This is extremely simple in this case. So this is like very trivial, but this structure is derived now not based on just intuition, but based on looking at the model. There's also the alternative of having this input static transformation and doing slave control on W. Remember that W is Q out. Looks essentially the same, except now this inverse static input transformation is going to be actually this thing here in this case. Again, it's very simple in this case because of the simple model. Now, okay, so if you look at a bit of what I've been doing here, so this is a fantastic approach. There's some limitation, of course, and the input transformation works best if you have a dominant dynamic equation involving the output of interest. So if you can have one, if I have one equation looking like this for the output and M is quite large, so you have the slow dynamics at the output, then it will, this method works well, but this does not always hold. And a couple of difficult systems. One is a heat exchanger. That's actually a difficult system, the example I showed, because there's no dominant dynamics in the heat exchanger. It's just a lot of cells that interact. So you can use the static transformation that I showed you. It works quite well, but it will only be correct at steady state, as we saw. Another bit difficult example is distillation columns. Again, there is usually not any dominant dynamics there, maybe except in the column ends. So we can again get some insight into how to control distillation columns by using the same approach. So I'm looking at composition control of distillation column here. I want to control the top composition using the reflux. So we can write down the mass balance for the reflux drum here. So that's the change in composition here is equal to what comes in, which is the V, the vapor flow, times YT. That's the top coming from the top of the column, minus what goes out. And that's V times Y. And so L plus D is equal to V. You note that this equation does actually not contain L at all. So there's no, you cannot solve this with respect to L. But the top composition, of course, depends on the reflux. So what you can do is imagine now doing is introducing W equal to YT, and then you would have like a cascade control of the top composition. So this is getting very close to what they do in practice. Now the top composition is not easy to measure because composition inside the column cannot be measured, but you can measure temperature, and then you can use the very closely related scheme of cascade control of temperature. So actually, by looking at this equation and doing a bit thinking, you can almost arrive that this is the right way to do things in a distillation column. Finally, a bit of discussion on feedback linearization and how this compares to what we've been doing. So feedback linearization is very powerful, but rarely used in process control, probably because of the limitations and complexity which people think are there. But actually the main idea is extremely simple, as I've been trying to show you in this presentation. And we have proposed extension to overcome these limitations, as I've been going through. Actually, these extensions are not really new. Maybe extent of extension 3 on static system, I didn't really see that, but the other extension you can find in papers. It's not in the standard feedback linearization approach, but you can find it in a lot of more application-oriented papers. For example, in this paper by Khalil that I reference here, you can find extensions 1, 2, and 5 shown. So this idea of using a tuning parameter is quite common. The using feedback control to invert the equation is used in practice. More general function for F is used. And all of these things make this much more user-friendly for practical applications. So we have also looked at many other examples, and in particular we have looked at the effect of uncertainty because this has been my main concern. This looks like magic, so it must have some problems. But what we have found that there hasn't really been any big surprises. It's fairly robust. And for this, I refer you to the master thesis by Callum Kingstree and Simon Bjorvan and ongoing work on this. So finally, the conclusion. So the basis for what I've been presenting is that we have a nonlinear process model for the output of interest. and we want to use this model to derive control structures. So the original input is U. So the trick now is to introduce this transformed input VA, which is the right-hand side F minus AY, or we can use this closely related one, which has the advantage of a steady state gain of identity from V to Y. So the resulting transform system from V to Y is linear and first order, perfect disturbed rejection, and decoupled if A is diagonal. Can also handle static models by using this right-hand side of the static model as the transformed input. So all of this is very simple, potentially very powerful, and to make use of it in practice, it's very useful to introduce cascade control of V or W, and particularly if you have this extra states, but also more generally, this approach can be used. So it then provides a systematic approach for deriving cascade control solutions. So that concludes my talk. So I hope you have some questions. Thank you very much for listening.
Thank you very much, Professor Skogestad. I'd like to ask the audience to please use the chat to indicate that you want to make questions or comments. So please, we are open now for questions and comments. Thank you very much, Professor. I think that your presentation is very interesting because you used the approach that it is common, as you said, to use blocks. People that work with process control typically use blocks. So we use this idea to kind of combine feed forward and feedback control and derive very interesting control structures. That's how I see. I don't know if you agree with me. So
yes, well, the main idea is to use the model, I would say. Use the linear model to derive control structures.
The linear model is a need, but when you use these transformations, you can get very interesting combinations that can improve the if you use it only a feedback controller. So we have already some people that want to make questions. Ajimiro is the first one that is interested in making a question. So Ajimiro, please, you have the word.
Okay, Mauricio, thank you. And thank you, Sigurd, to be here to sharing your ideas with us here. Pleasure. And also, I know Sigurd since he was in his sabbatical there in 1989 with Murari. I was there at that time. So I know him a lot of time. Sigurd, my question about your presentation today is, what's your comments when you compare what you show us today with the Hammerstein transformation for this nonlinear mapping and do the linear dynamic with nonlinear mapping? And what's the relation with these two approaches?
With Hammerstein, that I don't. I don't. This I haven't looked into. I can't really say. I mean, I think the closest for me is the feedback generalization approach, but I've never seen that I say this is really Hammerstein. But of course, there are static blocks there, but so that's similar. But I think
yeah, it's very similar. But naturally, depends on how you deal with this cascade control and how to deal with the nonlinear blocks to make the transformation. And I agree with you that
you have something called dynamic inversion.
The industry, the people does a lot of this nonlinear transformation, local nonlinear transformation for a set of variables or just a single variable. Do this nonlinear transformation, then apply a linear controller inside. So. There's some ad hoc application in the industry, yeah. So it's good to have some theory to explain what they are doing. It's a nice thing to do. But I think that for multivariable system with much more complex models and so on, I think this Hammerstein mapping seems to be more natural to deal with these more complex interactions and so on. And then try to do some control strategies to solve it. Well, just wondering about that. And another question is about how sensitive is this approach to model planet mismatch. You have told us that it's quite robust, but I think it will depend on the nonlinearities and so on, because this nonlinearity are explicit in this inverse problem. So it depends on the inverse gain that you have. If you have some mismatch, this will amplify this mismatching. So I'm not quite sure if these are robust for every case. This depends on the system and the nonlinearities. So what do you think about this?
Well, this has been my main also doubt about this, is the robustness. So there are some things, that's why we try to make this, are you seeing my screen now? You see, are you seeing my screen now?
Yes.
Yes, we have this inverse block here, for example. So in this case, there's no, so that's why I try to minimize the feedback from Y into this block, because we thought this was making a problem. But actually it turns out, you know, for example, if you're making the transform system slower, then you're using actually positive feedback, and it turns out when you use a delay in the system, actually makes the system more robust in some sense to gain error, for example. So because essentially the main problem in robustness comes from the feedback. So as long as you don't try to speed up the system too much by the transformation, there's no big problem.
Ingenious.
All right. And the last question, that what about when you have some multiplicity in the inverse problem? You know, you have many possible solutions for the steady state mapping, and how you choose the solution to apply in the inverse problem.
Yeah. Of course, then this is something that can create problems, but usually this multiplicity will be a problem also for any controller. It's usually a property of the system. It can make problems in transformation sometimes, but this is why I was recommending to solve them maybe by just feedback using integral controller, because the integral controller doesn't make any jumps in the U. It will just slowly change U. So it will not jump across a singularity, for example. So what you say is a problem that you need to take care of it, but I don't think it's a problem which is really special for input transformation. It's usually a problem coming from the control problem that you started with. So I think it can be solved in most cases.
Okay, thanks. I pass to the other in the audience.
Okay, Admiro, thank you. The next one is Professor Jorge Triweiler.
Hello, Sigurd. Thank you very much for your very nice talk. It was a great pleasure to look at your presentation. And my question is if I correctly understood your approach, you need to measure all the states. And then my question is related to the point, how you think that is necessary to use a state estimator to estimate the states, and how can we combine this state estimator with this approach?
Well, you don't need to measure all the states. Like there can be states hidden inside especially if you use Cascade control, you know, you can avoid that. It can be many dynamics which are hidden inside there. But you're right that I think definitely a state estimator can be helpful and can be combined. The paper I referred to by Khalil, he's using a state estimator in addition to make to make it possible to use this approach.
Yes.
So that's certainly something that's possible to do. That can be a good idea.
And you have made any tests related to a state estimator? Because
no,
all your examples are very simple. But if we increase the number of equations of your model, you have more states, and then I think that for the solution of the problem, the equation, the final equation, you need to have to include the state estimator in this approach.
Yes, there's many possibilities. Now, if you have very high order systems, you can use the static transformation, of course, like we did for the heat exchanger. So then you can have as many states as you want, because you can, if you know the equation, you can always solve them, because you have as many equations as you have states, essentially. And you just solve them and eliminate the states, because then you're eliminating all the states. Now, if you talk about the dynamic case, I really would say that it gets too complicated, and this is maybe not the right approach to use. I think the strength of what I present today is when you have quite simple models, but they still can be very powerful, because I've seen people using similar things in practice in industry. So I think just the thing that you can derive cascade control solutions and get ideas on this by looking at the model, I think is very powerful. When it gets really complicated, maybe I would go to a completely different approach, like nonlinear MPC or something, or I'm not saying that this approach should be used for everything.
All right, thank you.
Thank you, Jorge. I would like to ask the audience to feel free and make more questions. Please, questions and comments are welcome. Want to make any more questions or some comments? Yes. Sigurd, I was thinking, yes, I have one question. I will pass first to Rafael Ribeiro Sensio. Please, Rafael.
Hi, everyone. Good afternoon. Thank you, Professor Sigurd, for your presentation. I have a question, and I was wondering if the transformed system, which is linear, can be applied to an MPC controller to get a quadratic programming problem, because I think we can impose constraints on the transformed input V, but often we are interested on imposing constraints on the original input, which is U, and then maybe I think it seems that we are still having nonlinear equations to transform the constraints on V to the original constraints on U. So maybe we're still getting a nonlinear programming problem here, or you can get a quadratic programming problem. That's my question.
First thing, I think you're right what you're saying, that this approach does not really handle constraints well. So it's possible that you can make a combination with this and MPC. Now, of course, the MPC will be dealing with a linear system, and the U variable is going to be hidden inside there somehow, inside the transformations. And those are the ones who actually have the constraints. So I think it's an interesting question that you are raising. I don't know the answer to it. It seems reasonable that because the strength of this is with MPC is that you can consider linear models and constraints. The strength of this approach is that it considers nonlinearity and in a very good way when you have the model available and it's simple. So the combination could be very interesting, yes.
Maybe I can complete this question, Rafael, because we have a PhD student that defends his thesis some years ago, that's Simone Miyoshi. I think Sigurd knows her. And she did almost something like that. she made a nonlinear transformation in the input variables, then apply a linear MPC to solve the quadratic problem, and works quite well, this nonlinear transformation. So you use some nonlinear kernel to do the mapping, not to just invert the plant, but to do some nonlinear transformation based on some kernel, and then apply the linear MPC. So this worked well.
Okay.
Just to say one thing about what I present today, I think it's probably most useful to use in quite simple cases. Or the idea is that you can put this into a conventional control system quite easily, you know. So the blocks I'm showing here, they don't require much, no special blocks and no MPC. You can use blocks that are already available in any control system to do what I'm showing you today. And I think that's always going to be useful. So there will always be problems that may be more complicated, and then you have other tools. So this is like one thing for your toolbox. It's not solving all your problems, but it's going to be very useful for solving some of the problems.
Yeah.
And maybe makes a systematic approach to many of the things that people are using today.
Yeah, okay. I agree that. Yeah. Thank you, Professor.
Yes, thank you, Rafael. Sigurd, do you think that you could use also other blocks related to dynamic compensations, like, for example, I don't know, but in case of like a Smith predictor compensation or inverse response compensation, in terms when they happen, that would make it easier for the inversion?
Yes. This contains dynamic compensation already in an essentially optimal way. The reason we had this problem when I showed you maybe we had this delay, that's because we applied a static transformation to a dynamic system, so we're really not doing the right thing to begin with. Then, of course, you could imagine doing some corrections to it, like having some delays in the feed-forward block and all kinds of things.
Yes.
But again, I think if you get into that, then it gets quite complicated again. So
yes. Yeah, because it would become more and more blocks and yes. Yes, there is someone here that wants to make a question. Yes, please do it. But he is not with a microphone. But he is going to write the question, so you can read it, or I can read it too. Gabriel, please do it. You can write it. Okay. Yes. Can you read it? I can read it if it is not being shown to you.
Okay, I can read it now, yeah.
Okay.
One of the main appeals of this approach seems to be obtaining decoupled dynamics, but for that you need A to be a diagonal. If I understand correctly, you should have to use a Jacobian matrix of the system as A. Then how to proceed if the Jacobian is not diagonal? Okay, that's a good question. Well, in that case, you could select A to just be the diagonal elements of the Jacobian. Now, and it's really this picking it equal to the Jacobian was just one choice. You know, I don't think it's not that critical what you choose it to be. You shouldn't try to speed up the response too much, because then you get into problems with constraints and you get into problems with maybe instability. If you're slowing it down or not doing much change in dynamics, then I think it's fairly robust. So you can just make a diagonal, it's not a problem. Just take the diagonal.
Okay. Okay, Gabriel. So have we got any more questions or comments? Okay, Gabriel has thanked you. Well, there are many comments that people that like the presentation very much. Many people have written that in the chat. I think that it is very interesting. I have here present some undergraduate students, and I think they may be very, shocked by some of the things. Like, for example, we were teaching how to use, to describe the valve, and so you had that function of the nonlinearity, and they may be seen the way that very ingenious changed the approach, so that you use the flow rate instead of really describing how the valve behaved. So these students may be very touched by your presentation, because they know many concepts, and now you see changed the way the cascade control or the feed-forward controller can be integrated in the process controller control loop. So I think there is also this effect for the young students, and so I thank you very much, Sigurd. We will have this recording available so that other students can see it in the future. If someone else wants to make any more comment, please feel free. No, so yes.
I can make a comment to what you said about looking at the equations. So what this shows is that, it's not enough to be a control expert. You need to know the system. For example, you need to know that when you have a valve, that you have the possibility to measure the flow.
Yes.
So you need to combine control insight with insight into the system.
Yes, yes. So it's an approach that is very good, especially, as I said, for young students, that they have been in contact that soon, so that they can combine theory and those insights and the perspective of the system. So thank you very much. I think it was very instructive. I want to thank you in the name of our lab, LADES, and also GIMSCOP. Thank you very much. The audience is also thanking you. So I will pass the word for you, so that you can say your final words, and then when the word comes back to me, I will announce the next presentation.
Okay,
Yes.
well, I think I said my final words already. And that is that
Okay.
important to know the system that you're controlling. That's really what I'm trying to say here, to some extent. So thank you very much for listening.
Thank you very much. Our next presentation will be given by Professor Marcelo Lenzi. I think the title is in Portuguese. The presentation will be in Portuguese, but I will try to translate it. It's application of fractionary calculus to process system engineering. It will be on October 16. Okay. So thank you again very much. I hope to see you all next week, and thank you, Professor Sigurd, again. I will open to my colleagues to also thank and say some words.
Yes,
Admiro,
thank you
George.
very much again to be here with us, sharing.
Yes, I think he is with problems. Admiro is with some problems with the internet. Yes.
Yeah, I
think so.
You are not listening.
Now we are listening you. Yes.
Okay. Yeah, my internet's not good here in these days. But I was saying that thank you, Sigurd, again, for sharing his knowledge with us here. It's a lot of experience for practical application of control system with these ideas, simple and efficient ideas to solve hard problems, difficult problems. So thank you very much, Sigurd.
Thank you for listening.
I don't know if George, you want to say something?
Thank you very much, Sigurd. And I would like only to say that you are not the only fish that is going on the other direction.
Mm-hmm.
I think that we have more fish going on the other direction.
Hope to get some more fish following me, yes. I'm not completely alone.
Mm-hmm. It will begin a school of fish, as they say. So thank you all again. Thank you very much. I hope to see you, the audience, next week. And Professor Sigurd, I hope you can still continue meeting and, enfim, so learning from you. Thank you very much. Thank you.
Thank you. Bye now.